Okay, we're just going to go through a simple frame. I'm going to analyse this frame analytically, which means we're going to use maths to find out the reaction forces here and here, reaction force 1, reaction force 2, or A and B if you prefer, and we're going to find the forces in the members and whether they're in compression or tension. So the first thing we're going to do is we're going to find out the reaction force, and to do that we're going to do moments. So we've just got a quick moment diagram there. So our force, our load, is halfway along, just as it is here, and we've got a reaction force 1 and a reaction force 2. Okay. So the thing that we do then is we pick a point we're going to take our moments about. So let's take our moments about one of our forces. So there. I've just circled the point there, reaction force 1. At this point, we might ask, what is a moment? Well, a moment is a force times a distance. More specifically, a force times a perpendicular distance. Perpendicular just means at right angles to. So the distance is at right angles to the force. So there's our force. So our distance is perpendicular at right angles to. So because we're taking moments about that point there, then the distance from the point to the force is 0. And any number multiplied by 0 is 0. So effectively this force falls out of the moment equation. So we toddle along, there's our first force. So what's the distance? Well, it's going to be half of 8.5, so that's 4.25. And then our second force is our unknown reaction force, and that's at 8.5 meters. So the first thing we do is we identify whether we've got clockwise or anti-clockwise moments. And here we've just identified whether they're clockwise or anti-clockwise moments. If you're struggling with that, just pick up a pencil and hold it by the left hand side, just loosely between your finger and thumb, and just press up or down. And if you push down in the middle, you'll see that your pencil is turning clockwise. If you push up at the end, you'll see that your pencil is turning anti-clockwise. So just if you just need to help yourself get your head around that. And with more complicated beams, that might be something you want to do. So why do we identify our moments? Well, for something to be in equilibrium, 3 things have to be true. The up forces must equal the down forces. The left forces must equal the right forces. And the anti-clockwise moments must equal the clockwise moments. So that's it's a slightly odd thing to say, isn't it? That up equals down, left equals right, and clockwise equals anti-clockwise. But what we're actually saying is that if we have every action has an equal opposite reaction. So if we have a load here, there must be equal and opposite reaction forces that stop the load moving. If we didn't have equal and opposite reaction forces, then we'd have movement. Yeah? So if you go walking across a very muddy field, you might find yourself sinking into the mud because the mud doesn't have enough of a reaction force to stop you sinking. If you're on a bouncy castle or trampoline, then you have a greater reaction force and you get thrown up into the air. Okay, but when we're just walking along the road or the pavement, we have an equal and opposite reaction force because we don't bounce up and we don't sink. So let's take our moments. So we're going to say from this point here, it's 4.25 meters to a 36 Newton force. That gives us a clockwise moment. And that must equal this reaction force times by 8.5 meters. So let's put that in equation and see what that looks like. So here I've just put that information in an equation. So 36 newtons times by 4.25 meters equals R2. That's our reaction force 2 there. That's our reaction force 2 there. Remember, times by 8.5 meters. Okay. So our next line, all I'm going to do is just multiply 36 by 4.25. So that gives us 153 equals 8.5 R2. So we've just tidied that up a little bit. So now we can find R2 quite easily. We just need to move that 8.5 over the equal sign. So that's 8.5 times by R2. So if you remember what we do to one side, we do to the other. So we want to get rid of that 8.5 on this side, on the right hand side. So we can say 8.5 divided by 8.5 gives us a 1. We do to one side, we do to the other. So essentially we bring that down and it becomes 153 divided by 8.5. So let's just have a look at that. So there we go. So all that's left now is to divide 153 by 8.5. And so that gives us an answer of R2 equals 18 newtons. which, to be fair, we could have probably worked out without going through this, because 36 divided by 2 is in fact 18. And we expect, because this is in the middle, to have an equal split between our reaction forces. But this is just an example of how to work through it. Okay, so now you could think, well, what we need to do is we need to take moments about there, and we'll do it in the other direction. But certainly for more complicated examples, that can be effort. There's a much simpler way of doing it. So if you remember, I said that our three characteristics of equilibrium were up equals down, left equals right, and clockwise equals anti-clockwise. So we can take that first rule and we can say, well, up equals down. So there's our up forces. So our up forces must equal our down forces. So let's see what that looks like. So we can say that our reaction force 1 plus our reaction force 2 must equal our down forces, which is our 36 newtons. But we know that reaction force 2 equals 18. So let's put that information in our equation. And now, hopefully, straight away we can see that, some of you have probably already done this already in your heads, that all we need to do is to subtract 18 from 36 to find R1. And of course the answer is obviously 18. So, which is, again, exactly what we'd expect. Yeah? Again, it's a simple example. So we found our reaction forces R1 and R2. So I'll just fill that in here just for the sake of completeness. So R1 and R2 equal 18 newtons. So now we've found our reaction forces, and we can now focus on finding the forces in the members and whether the members are in compression or tension. So what I'd probably do now is I'd number the joints so that we all know what we're talking about. So joint 1, joint 2, and joint 3. Okay, just so that we can say, on joint 1, on joint 2, and joint 3. It just makes life a little bit easier. And we're going to focus on joint 1. We could, in this instance, we can start on any of the joints, because we can only select a joint when it's got 2 or less things we don't know. Well, we know one thing, we don't know one thing, we don't know 2 things. We know one thing, we don't know one thing, we don't know 2 things. So, and the same at joint 3. So we could start with any of these joints, but in a more complicated example, the only place we can start is at the reaction forces. So that'd be joint 1 and whatever joint's at the other end of the structure. Okay. So we're going to start at joint 1. So as always, I'm going to draw a quick sketch so that I know what's going on, what I'm focusing on, and what I'm looking at. So here's my quick zoomed in sketch of joint 1. Just so we know what's occurring, what's going on. And we know this is a 60-60-60 triangle, so we know that that angle there is 60 degrees. Now, the first thing we do is we make an assumption, and we assume that for things we don't know, the forces are moving away from the joint. So we assume tension. We assume that the members are in tension until we find out otherwise. So now we're back to our 3 laws of equilibrium. Up equals down, left equals right, anti-clockwise equals clockwise. And in the problems that we've got at this stage, we only really need to consider the first 2 of these, up equals down and left equals right. So for this joint here, let's start by saying up equals down. So what forces have we got going up? Well, obviously we've got the 18 newtons going up. Is anything else going up? I think it's fair to say that the upwards diagonal here is also going up. It's not going vertically up, but at least some of it is going up. Some of it's going along to the right, but some of it is going up. How much of that is going up? Well, we need to find out, and to do that, we need to do a little bit of trig. So I'm just going to cut away from the main problem for a moment, and we're going to talk triangles. So here's a nice right angle triangle. Obviously we've got a vertical line here, and we've got a horizontal line on the horizontal. So let's just identify those a bit more. There, we can give them separate colours then. Should we give them separate colours? How about a nice yellow? Yeah, let's do that again. purple. There we go. So we've got a purple horizontal line and a yellow vertical line. And we've got a hypotenuse, which is black. So the question we're asking then is, if this were our force, or indeed if this were if this hypotenuse here was our force, doesn't make a lot of difference, does it? Then how do we find how much of that force is vertical and how much of that force is horizontal? Well, we could find the vertical side of this triangle, couldn't we? And to use that, we'd use SOHCAHTOA, sine, cosine, and tangent, sin, cos, and tan. So to find that out, we'd say sine theta equals opposite over adjacent. I'll be honest, I'm regretting that yellow colour now. Let's go for... No, that's too close to the other one, isn't it? Let's go for a nice blue. There we go. Let's go for a nice blue. Okay, that's easy to see, isn't it? So sine theta equals opposite over adjacent. But what we want to know is, what is that opposite side? What is that opposite side? Yeah. Well, to find the opposite on its own, we'd move adjacent over the equal sign, so we'd have adjacent. Come on, Steve. Just testing you there if you're paying attention. Hypotenuse. We'd move the hypotenuse over to the other side. So we'd have hypotenuse multiplied by sine theta, where theta would be this angle here, or in this instance, this angle from the hypotenuse to the adjacent is the angle that we're talking about here. Okay, so let's just rearrange that. So the hypotenuse times by sine theta is the vertical component. It is the opposite, which is our vertical component just here. So we need to just hold on to that. Hypotenuse times by sine theta. Okay, and similarly, if we were going to find the horizontal component, well, we'd use cosine. So let's just have a quick look to see what that looks like. So here we can see that cosine theta equals adjacent over hypotenuse, as we all know. So again, we take the hypotenuse over to the other side, so we get hypotenuse times by cosine theta equals the adjacent. So hypotenuse times by cosine theta is the horizontal component of our hypotenuse there. Okay, and that's true whether our triangle faces this way or whether our triangle faces this way. So let's take this information back to the problem that we're trying to solve. So you can see I've put some nice colours on our forces. So we've got the yellow force, the green force, and our reaction force is a nice blue colour. So because colour should never be our only form easy for me to say. Because colour should never be the only form of coding, what we're going to do is we are just going to put in, we're going to label these, we're going to say F1, and we're going to say F2. There we go. Okay, so force 1, yellow, force 2, green. So we're going to apply now our rules of equilibrium. We're going to say up equals down, and we're going to work out what our up forces are. So that's 18 plus the vertical component of F2. And then we're going to say down. Alright, let's do that. Okay, so I'll try to keep things colour coordinated as we go. So let's start with that 18. Let's start with that 18 Newton force. So let's make that nice blue colour. So 18 up, and then we've got a plus the vertical component of F1. So if you remember, we said that was the hypotenuse, so we're calling the hypotenuse yellow. I'm calling the hypotenuse F1. Yeah, that's not yellow, is it? We need it to be orange. There we are. F subscript 1. Okay. Come on. There we are. So F1, and then if you remember, we said that that was sine theta. So let's make that nicely colour coordinated as well. So 18 plus F1 sine theta, because that was the vertical component of our F1 force there. Okay. And that must equal, he says, the down forces. Now we look at this, what are the down forces? Well, there aren't any, are there? There's nothing pointing down. There's no arrows pointing down on this diagram. That's not pointing down, that's not pointing down, that's not pointing down. So, 0 is, as always, a valid answer. So let's fill some numbers in that. Well, we know sine 60. But the only thing we don't know in this equation then is f1. It's the only thing we don't know. So we can rearrange this equation to find f1. So it's f1. So let's move the 18 across first. Well, it's plus 18. So that would move over to become minus 18. The next thing we'd have is f1 multiplied by sine theta. So we divide by sine theta and that would move it across. What we do to one side, we do to the other. So we get f1 equals 18 divided by sine theta. So let's just have a look, see what that looks like. So you can see we've moved things across the equation there, and we're left with f1 equals minus 18 divided by sine 60. So I've just put the 60-degree angle in there, 60-degree angle from there to there, from there to there, on our 60 degrees all the way. Okay, so now we can calculate f1. So some of you might know. So, well, let's find out, shall we? Let's do it step by step. Okay, so I just calculated the sine 60 there. You can just do minus 18, missed my minus sign, minus 18 divided by sine 60, or you could do sine 60 first and then calculate that and use your calculator to save that answer of sine 60 and divided by minus 18. I personally just type minus 18 divided by sine 60. I'm just expanding things a little bit more there. Okay, and that gives us an answer of minus 20.78 newtons. So now we know the force in F1. Okay, so now there's a minus sign there. Now, as we know, we don't get forces, we don't get negative forces. We can't get negative forces, but we can get forces in the wrong direction. Okay, so instead of it being in tension, that tells us that it's actually in compression and is moving towards the joint. Okay, so with this new information, we just change our diagram. So we're going to use this diagram now for our left equals right, and we might as well take this new information with us. Okay, so let's do a left equals right. So once more, we'll go around the joint asking, well, what goes to the left? Well, that's not going left or right. That is going left. Okay, and is there anything going right? F2 is going right. So the horizontal component of F1 must equal F2. So let's have a look. If we remember, back here, we said that our horizontal component was the hypotenuse times by cosine theta. So let's employ that and let's see where we go. So once more, carrying on with the colour coordination, we've got a nice yellow F1 cosine theta must equal F2, because the only thing going left is F1 and the only thing going right is F2. So we know it's cosine 60, so let's put our numbers in. So we've filled in F1 as 20.78, there it is, 20.78. If you've got that answer saved on your calculator to 30 decimal places or whatever your default calculator saves to, then please use that number. You'll get a more accurate answer. It does make a difference. Always do your calculations to 3 or 4 decimal places, write them down to 2. That's fine. But never any less than that. Okay. And when you've got memory buttons on your calculator or it remembers the last answer, then do it to as many decimal places as your calculator will allow. So there's our force, 20.78 over here, 20.78, and of course cosine 60 because it's a 60-degree angle because it's an equilateral triangle. And so all we do is plug that into our calculator. 20.78 multiplied by cosine 60 equals F2. And so we'll just fill that in for completeness. And so we plug that into our calculator and we get F2 equal to approximately 10.39 newtons. Just remember, whenever you get an equal sign, whenever you've found out what you're finding out, you always need a unit after it. So in this case, we've just found out a force, so the unit of force is newtons. And that's it. We are done for this. Let's just finish this off. So there we go. F1 is there. F2 is here. So let's put that there. And so we found out F1, and we found out F2, and we found out that F2 is in tension because it's going away from the joint, and we found out F1 is in compression because it's going towards the joint. And because this is a symmetrical system, we can assume that the force here is the same as the force there, so we don't have to go pick another joint for joint 3. We'd have to do joint 3 or joint 2, because we know this and we know this. So we know that that is 20.78 and in compression, and we know that that is 10.39 and is in tension. And that's a brief introduction onto how to analyse a simple frame graphically. The next video will be for a more complex frame, and we'll go through that maybe a little bit quicker. Thank you very much.